All right, yeah, see you. All right, good morning, everyone. Hope you're doing well. Friday, weekend's upon us, so that's good. There is the Prairie Learn homework due today, and then we will be doing lab 7 next week. There is going to be a pre-lab, so please get that done before your section starts. And then finally, as you know, we're going to be doing our Prairie Learn quiz on Wednesday. Okay, good. So what we did last time is we finished off our discussion of analyzing circuits with resistors and batteries and combining resistors in series and combining resistors in parallel. And then we started our discussion of magnetism. And one of the things that we discovered is that magnets always come in pairs of north and south poles. So we never have like an isolated north pole like we could have, say, an isolated positive charge. So that means if we have something like a bar magnet, it's always going to have a north and a south pole, and magnetic field lines are going to exit the north pole. They're going to loop around and then re-enter into the south pole of the bar magnet. And then the other thing we started to think about is, well, how do charges and magnetic fields interact? Or what's the relationship between charge and magnetic fields? So we started by placing a compass, and a compass is like a little bar magnet. It's on a low friction bearing, so it rotates to point towards the north pole of the Earth due to Earth's magnetic field. And so the first thing we did is we placed that compass next to a wire, and nothing happened, right? The compass needle still points to the north pole of the Earth. Then what we did is we placed some charge on that wire, static charge, so it's just charge that's not moving. And once again, it had no effect on the compass. It still points north. The last thing we did at the end of Wednesday's class is we imagined, well, what if we placed a current in that wire? And so a current is just moving charge. And in that case, we saw that actually placing a current in the wire did cause the compass needle to rotate. It got deflected away from its initial orientation. And so our conclusion is that currents or moving charge is a source of magnetic field. It creates a magnetic field that exerts some force on the compass needle and causes it to rotate. So what I want to do today is I want to continue with that. And so let's continue to imagine our wire with a current through it. So let's continue with thinking about a compass next to a wire with a current I. And in fact, this time what we'll do is we'll have our wire with a current, and then we're going to take the compass and we're going to place it at different positions around this wire. So here's going to be our wire. There's current I in this wire. So we can just imagine that this is the long wire. I'm just drawing a section of it. And so the first thing we'll do is we'll place our compass over here. And what we'll find is the compass needle points in that direction. And then we'll place our compass over here, and we'll find that the compass needle will be in a different direction. It'll be something like this. And then we'll place a compass over on the right-hand side, maybe out front, and the compass needle will this. And then we move it a little bit behind, and let's place one last one. So this one's sort of supposed to be a little bit behind the wire. And if we look at all the orientations of the compass needle, we can kind of draw a dashed line that shows kind of roughly the path that they're following. And what we would discover is that these magnetic field lines, which are causing the compass needle to change its orientation, are looping around the wire. So the current creates a magnetic field B that loops around the wire. And so this magnetic field causes the compass needle to align with the field due to the current. And so what I'm imagining here is the magnetic field of the Earth is very weak. And so what we're going to do is we're going to place a large enough current that it completely dominates the Earth's magnetic field. And so the compass needle is determined almost exclusively just by the magnetic field of this current. Okay, and so what we can do is we can replace this dashed line with a continuous line that represents the magnetic field of that's due to the current. And so here, I won't block the orientation of the compass. And this magnetic field loops around, it turns out, in this direction. If we were to reverse the direction of the current, so instead of it going upwards, it was going downwards, we would still have magnetic field lines that loop around, but it would be in the other direction. And so instead, so this, in this one, if I look from below, it's going clockwise, I guess. And then if we look from below and we reverse the direction of the current, this field would point counterclockwise. And the compass needles would flip their directions by 180 degrees. So let's just make a note of that. If we reverse the direction of the current, the magnetic field changes direction, and the compass needles would rotate by 180 degrees. So what we need is, we need a little rule that would tell us, for a given direction of current, what is the resulting magnetic field direction? And so there's a right-hand rule for doing this, and it's very easy to use. All you have to do is you place your thumb in the direction of the current. So in this case, our current is going up. So thumb points up, and then your fingers curl around naturally in a certain orientation. And so it's important that you do this with your right hand, because if you do it with your left hand, you'll get the opposite direction. Okay, so my finger goes up, and then, so what that tells me is that my fingers curl around, and on the left-hand side of the current, my fingers are pointing out of the screen. And so there, the magnetic field is coming out of the screen, like we've drawn, and then the fingers would curl around so that on the right-hand side, they point into the screen, and so that gives the orientation of the magnetic field. So to find the correct direction of the magnetic field due to a current, we use the right-hand rule. So right-hand rule, and I'll use RHR for a shorthand for right-hand rule. because we're actually going to find that we have a few different versions of right-hand rules for different scenarios. So this one is for determining the direction of the magnetic field due to a current. Okay, so what we're going to do is, one is we're going to point the thumb of the right hand in the direction of the current. And two is we just look at the direction that our fingers naturally curl. So our fingers naturally curl in the direction of the resulting magnetic field. Okay, so let's try this. Let's pick a different kind of scenario. And so we'll just have a wire. It doesn't need to be straight. It could be kind of whatever shape you like. And so this is going to be a current carrying wire. And so let's imagine that over here, we have our current I. Maybe it's going from left to right in this case. And so I want to know the direction of the magnetic field. All we have to do, and I encourage you to practice this, is, there's no shame in putting your hand up, right? No one's going to think anything less of you if you do it. So you put your thumb in the direction of the current, your fingers curl around. In this case, my fingers above my thumb are pointing out of the screen. And so that means the magnetic field is looping around such that it's coming out of the screen above the wire. And then if I wrap my fingers around like this, my thumb is still pointing to the right. Now my fingers below my thumb, which is below the current, below the wire, are pointing into the screen. And so below, we have the magnetic field pointing into the screen. Of course, I could also curl my fingers so that they're out in front of the screen a little bit, and that way they're pointing down. And then it's hard to do, but I can do it like this. Now my fingers are behind the screen, behind the wire, and they're pointing upwards. And so you get this looping around of the magnetic field. Of course, if we were to change the direction of the current, so that my current, let's imagine that it was pointing left, then my fingers would just obviously curl in the exact opposite direction. Okay, so that's the right-hand rule. And so what we're going to essentially be doing, so we now have a bit of evidence, like you could do this easily at home. If you had a compass and say some wires and like 9-volt battery, you could put your compass next to your wire. As long as you get a strong enough current in that wire, you should see that it has some effect on the direction of the compass needle. Okay, what we're going to be doing for the next few classes is the following. Let's think of an analogy with what we did at the beginning of the term. At the beginning of the term, we established that charges are a source of electric fields. Now we've established that a moving charge or current is a source of a magnetic field. We then said, okay, back to the beginning of the term, we have a charge, it creates an electric field. That electric field can then exert forces on other charges. So what we're going to do is we're going to say, okay, I know now that moving charges or a current create magnetic fields. Those magnetic fields can then go exert forces on other moving charges or other currents. And so what we're going to be dedicated to over the next few classes is, one, given a current, can we figure out mathematically what that strength of that magnetic field is and what its direction is? And so we've talked a bit about the direction already. And then once we have that magnetic field, can we then go figure out what force it exerts on other moving charges or other currents. So that's the path we're going to take. Okay, so let's begin by seeing if we could figure out something about the strength of the magnetic fields that currents generate. So let's imagine a point charge Q moving in a straight line with velocity v. So what we'll first do is we'll figure out what the magnetic field due to a single point charge moving with some velocity is, and then we'll use that result to try to deduce, okay, if we expressed the moving point charge as a current, then what magnetic field how could we express that magnetic field in terms of the current? All right, so I'll draw a dashed line. This dashed line represents the path that our point charge is going to follow. We'll start with a straight line path. And so here's our point charge Q. We'll make it positive. And we'll draw a velocity vector. So it's moving along this dashed line with some speed v. And the question is going to be, if we go out to some point P over here, where this is the position vector from the charge to that point P, the question is, what is the magnetic field B at P due to the moving charge? Okay, and we're not going to derive this from anything fundamental. All these results are based on observations, right? So in physics, what we do is we make some observations of some natural phenomenon, and then based on those observations, we kind of deduce some mathematical way of representing that effect. And then we try to figure out, okay, what are all the consequences of that effect? So the observations that we would make if we could set something up like this is the following. So we would find that the strength of the magnetic field B at P is proportional to, there'll be a number of factors. Okay, the first one is, what we could do is to find the magnetic field at P is maybe we place a compass there, and somehow we design a little apparatus that measures the torque on the compass needle, like how strong is the twist on that compass needle? And that would tell us something about the strength of the field, okay? And so we set this up and we do this measurement with charge Q, and then we do the exact same measurement where we replace Q with something that is twice the charge, so 2Q. It's moving in the same direction with the same velocity, and it's starting at the same position, same distance from P. If we double the charge, we'll find that the strength of the magnetic field doubles. If we cut the charge in half, the strength of the magnetic field would be reduced by a factor of 2. And so one thing that this the magnetic field is proportional to is the charge Q. Okay. And so the next thing we do is we say, all right, now I'm going to keep the charge always the same, but I'm going to change its velocity. When I make it move twice as fast, the strength of the field doubles. When I make it move with half the speed, the strength of the field goes down by a factor of 2. And so it is proportional to the speed v of the charge. Okay. The other thing we could do is we say, all right, I'm going to keep Q fixed. I'm going to keep the velocity fixed. Now what I'm going to do is I'm going to increase the distance from P. So I take the distance R from my point charge to P and I double it. And what we'll find actually in that case, the magnetic field would go down as we move further away from the moving charge, but it won't go down in proportion to the distance. It'll go down in proportion to one over r squared. So if I double the distance, the strength of the field would go down by a factor of 4. If I halve the distance, the strength in the field would go up by a factor of 4. Okay, so it is proportional to 1 over r squared. The same thing would happen for our compass needle around that wire. If I took my compass and moved it farther away from the wire, it would still align with the field, but the torque on the needle would decrease. So as you move further away from currents or from moving charges, the fields, the magnetic fields they produce get weaker and weaker and weaker. Okay. And then there's actually one more thing that we can do. And that is we can change the angle between the velocity and that position vector r. And so this is perhaps the one that is a little more unfamiliar and a little bit surprising, is that the magnetic field also depends on that angle theta. And the way it depends on it is that it depends, it's proportional to the sine of theta. Okay, and so this result is perhaps a little surprising, or maybe less of a familiar result, something that would be harder to guess. We might have guessed that a bigger charge makes a bigger magnetic field. We might have guessed that a charge moving faster makes a bigger magnetic field because that would correspond to a larger current. We probably would have guessed that as we move further away from our moving charge, the field gets weaker. It's probably a little more tricky to guess that it depends on the sine of this angle. That's weird because what's the sine of 0? 0, that's right. And so if the angle was 0, then that would mean that we would have a point right along this dashed line. And what this is telling us is that right along this dashed line, the magnetic field due to this moving charge would be 0. What's the sine of 90 degrees? 1. And that's sine of 1, or sine of 90 equals 1. That's the biggest possible value. And so what that tells us is that for a fixed r, the magnetic field is strongest exactly perpendicular to the path that the charge is following. Okay, so if we summarize all of these results, what we're going to find is that the magnetic field strength is proportional to the value of the charge, how fast it's moving, 1 over the square of the distance from point P to the charge, and as well as this factor of sine theta. Okay, and so let's try to draw the effect of the sine theta, because that's probably the least familiar of these results. So here's our Q. We'll draw our velocity vector again. Here's V. All right. And so what I'm going to do is I'm going to draw a bunch of different points P. They're all going to be the same distance away from Q. So I'll keep that R value fixed, the length fixed. But I'm just going to change the angle. And so the first thing we'll do is we'll draw an R vector here, and then we'll say at this point, B is equal to 0 because, because theta is equal to 0 and sine theta is equal to 0. Okay. The other one we could do is I'm going to try to keep R the same. So I don't know, it's roughly something like that. And here's another point. And over here, what we would say is, let's see, theta is equal to 90 degrees because we're going to be, in this case, perpendicular to our velocity. And sine theta is equal to 1, which is the maximum possible value. And so that means the magnetic field is a maximum at this point for whatever this value of the distance R, whatever the length of R is. Okay, and then of course we could have a bunch of intermediate values. So I could have one over here, where here's another R, and here's our point P. And so here theta is between 0 and 90 degrees. And we have that sine of theta would be some value between 0 and 1. And so we would have the magnetic field somewhere between the maximum value and 0. Okay, I won't draw it, but we could also have, you know, theta doesn't have to be just between 0 and 90. We could have theta is, I don't know, 200 degrees or it could be like 150 degrees or something like that. Well, okay, maybe we will draw one. Let's see, maybe what I'm going to do is, let's see if I can move things around a bit. So this is going to be our point was over here, and these things correspond to that point. Okay, so we could have some other position vector over here, R. This is some angle between 90 and 180 degrees, and we would have, let's see, theta would be between 90 and 180. Sine of theta, what does sine of theta go between 90 and 180? What's its range? So sine of 180 is still 0, right? And so it's still going to be between 0 and 1. And so our magnetic field would still be between its maximum value and 0. So in fact, if, well, yeah, okay. So that's all I want to say, is that we also have magnetic fields following behind the moving charge. Okay, good. So we know that B is proportional to QV sine theta divided by R squared. What we want is to find the constant of proportionality. And the only way to do that is to do a series of careful measurements. Those measurements are actually pretty difficult because the magnetic fields that are going to be generated by a single moving point charge are very weak, okay? But you can, in principle, do these experiments carefully. And so through careful measurements, we can find the constant of proportionality, and the constant of proportionality is written as mu naught over 4 pi. It's a bit of a weird way to write it, but that's what we're stuck with. And so it's mu naught over 4 pi times QV sine theta divided by r squared. So this is our constant of proportionality. Mu naught is called the permeability of free space. Okay, for us, I mean, I don't really care what it's called, but that's its name. It's just a constant, and its value is mu naught is equal to 4 pi times 10 to the minus 7. And then it has units of Tesla, meters, divided by amps. So that means the entire constant, mu naught divided by 4 pi, is just equal to 1 times 10 to the minus 7 Tesla meters per amp. Okay, so it turns out that if you were to do a unit analysis of this magnetic field, let's see, well, why don't we just do it? The units of magnetic field are going to be the units of mu naught times the units of QV over r squared. We don't have to include sine theta because sine theta is just a number. It doesn't have any units. So in terms of unit analysis, this is what we have to do. Let's see. Mu naught, we just wrote down, is Tesla meters per amp. Q is measured in coulombs. V is a meter per second. And 1 over r squared is meter squared. Okay, so let's see what we could do. We have 2 meters in the numerator. That cancels with the meter squared in the denominator. And then we have a coulomb per second. What's a coulomb per second? Amp, that's right. Current was equal to the change in charge divided by the change in time. So it's coulombs per second. And so these coulombs per second cancels with the amp. And all we're left with is this unit Tesla. So magnetic fields are measured in units of Tesla. Tesla, of course, is the name of a fairly famous scientist who studied a lot of these magnetic effects. And I mean, I'm sure you've all heard of Tesla. And so I don't know actually when he was active, but like hundreds of years ago, I assume. Okay, so that is the strength of the magnetic field due to moving charge when the charge has some velocity v. The problem with this expression that we have here is it's an expression only for the strength of the magnetic field. It doesn't have any direction information in it. So what we'd like to do is we'd like to revise this expression so that we can incorporate some direction information. In order to do that, we're going to have to introduce a new type of product, and it's called the cross product. So let's do cross product. Have you guys come across cross product in any other courses? Yes, a few people. Who hasn't seen cross products? Okay, so it's going to be new for probably the majority of the class. So let's just do this carefully. So the cross product is a product between two vectors. Okay, before we go and define the cross product, why don't we first just recall the dot product between two vectors, and then we'll see some similarities between the two. Okay, so let's first recall the dot product between two vectors. All right, so I'll draw two vectors in the plane of the page. So we'll have some vector A and then another vector B, and there'll be some angle theta between the two. Okay, so the dot product was A dot B was equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And then, of course, the magnitude of A is just the length of A, and we could just denote that as A times B cos theta, where when we don't draw the little vector sign over A, what we mean is just the length of that vector, and we disregard any direction information. Okay, so one thing we can do is we can note that the result of the dot product between two vectors is a scalar, or it's just a number. So it has no direction associated with it. All right, so fair enough. That's the dot product. So what's this cross product all about? So the cross product is going to be, here, we'll keep that up there. So cross product. We'll just draw the exact same scenario. So we're going to have vector A, then we'll have some other vector B, and there's some angle between the two. So the cross product is A, and then the symbol is just this little X. It looks like kind of multiplication symbol, but this is not ordinary multiplication that you would do with, like, say, it's not the same as 2 times 4 is 8 or anything like that. Okay. The first thing we're going to do is we're going to just focus on the magnitude of the cross product. So let's just do this. So this is going to be the magnitude of the cross product. Does anyone have any guesses? So if the dot product is AB cos theta, what would we do for a cross product? What would you just guess? AB sine theta. That's exactly what you're going to do. Okay, so AB sine theta. All right. That's right. So let's do a bit of an interpretation of this AB sine theta and AB cos theta. Okay, so we'll go back up here and we'll say, let's think about B cos theta. So what I could do is I can construct a right angle triangle. And so now I have a right angle triangle where the hypotenuse is length B. And so what is B cos theta? Is it the opposite side or the adjacent side? Right, so the triangle we have is B theta, and where's cos theta? Is it this bottom side or is it this vertical side? The adjacent, that's right. So the adjacent side, and so this is B cos theta. And so what we're finding here is this is B cos theta. Is selecting the component of B that is parallel to vector A. So the dot product selects the component of B that is parallel to A. Okay, so what you probably might guess is that for the cross product, which involves the sine of theta, is it's going to select the component of B that is perpendicular to A. And that's exactly what it's going to do, because I can construct the same right angle triangle, and I can say, well, this is B sine theta, and here's B. And so this B sine theta is selecting the component of B that is perpendicular to A. So the cross product selects the component of B that is perpendicular to A. All right, so in some ways, the dot products and the cross product are complementary to one another, just selecting either the parallel or perpendicular component. There is one important difference that we haven't addressed yet, and that is the result of a cross product is not a scalar, it's actually another vector, okay? So one important difference, important difference between dot and cross products is that the result of the cross product is another vector. Okay, so what we've written above here is this result is just the magnitude of the cross product. Okay, so in general, A cross B results in a third vector. And so we already know some properties of this vector. The first thing we know is that the magnitude of this vector C is AB sine theta. Okay, so we've already established that. The last thing we need to do is establish the direction of this vector. And that's where we're going to require another right-hand rule. Okay, and so this one is the following. So the first thing we could do is we could say the direction of, well, let's say it this way. Vectors A and B form, or let's say they lie in a plane. Lie in a plane. And so I'll draw the same picture that we've drawn a couple of times already. Here's vectors A and B. In this example, the plane that they lie in is the plane of the screen or the plane of the page that you're drawing on, like so. So in this case, the plane is the screen. Okay, the direction of C is going to be perpendicular to both A and B, or in other words, perpendicular to the plane that A and B lie in. Now, perpendicular to that plane, I could have it coming out of the screen, or I could have it going into the screen. So all we need to do is to determine whether C is pointing into or out of the plane that A and B lie in. So C will be perpendicular to this plane, or equivalently, C is perpendicular to both A and B. So to determine whether C is into or out of the screen, we use a second right-hand rule. Okay, and so before I write it down, I'll just show you what this right-hand rule is. We have two vectors, A and B. If C is going to be A cross B, then A is the first vector in the cross product. So the way I do the right-hand rule is I just take my whole right arm and I put it in the direction of A. Okay, and so A is horizontal right now, and so I'm going to put my right arm horizontal. And then what I'm going to try to do is I'm going to try to curl my fingers so that they end up being parallel to B. And so B is kind of sloping up a little bit like this. And so I'm going to take my fingers and I'm going to slope them up. And my thumb tells me the direction of C. And so my thumb's pointing out of the screen right now. And so that means C is out of the screen. Okay. So let's see. So this right-hand rule is the following. So step one is place your right hand / arm in the direction of A, which is the first vector in the cross product. So that gives us a bit of hint that already that A cross B and B cross A are not going to be the same thing. Okay, so it matters the order of the vectors in the cross product. Okay, so the second step is to curl the fingers of the right hand so that they are parallel to B, which is the second vector in the cross product. Okay, and then finally, the last thing you do is just look at your thumb, and your thumb points in the direction of C. Okay, let me draw it again so I can have all of this stuff on the screen at once. So here's A, here's B, and let's see, let's just do it again. A is horizontal and to the right. I curl my fingers so that they're kind of roughly parallel to B. My thumb points out of the screen. And so we would say C equals A cross B points out of the screen. Let's just for practice, let's try to make a vector D, which is equal to B cross A. Okay, so we'll just apply the rules. So I'm going to place my right hand in the direction of the first vector in the cross product. So that's B. So B is something like this. And now I'm going to try to make my fingers parallel to the second vector, which is A. That's horizontal, so I'll make my fingers horizontal. Now my thumb points into the screen. Okay, and so D points into the screen. Okay, so A cross B and B cross A result in vectors that are the same length, the same magnitude. It's always going to be AB cos or AB sine theta, sorry. The difference will just be the direction. They'll be anti-parallel to one another. Okay. All right, so let's see if we can return. Oh, I guess we're done. Okay, so we've run out of time. What we're gonna do next time is we're gonna combine our expression for the strength of the magnetic field due to a moving charge with this stuff we know about cross products, and we'll write a vector equation for the magnetic field that results from a moving charge. All right, good. Thank you very much.